There are a number of different ways to look at a solution to a problem like this. One of the things that we can do first is to draw some graphs of the motion, just like the same velocity, acceleration, and position versus time graphs that we were drawing before. So first, let's draw an acceleration versus time graph, since that's what we're given in terms of the initial conditions of this problem. So I start off with an initial acceleration of 3 meters per second squared. And then at some point, 30 seconds into the motion, my acceleration drops to 0. So if I draw that on a graph, my acceleration is going to look like this. It's going to be constant until I get to 30 seconds. And then it's going to drop down to 0. And it's going to be 0 for the rest of the motion. Okay. So now that I have that acceleration versus time graph, we can draw a velocity versus time graph. So velocity versus time, since we have constant acceleration in that first part of the segment, the velocity is going to increase linearly from 0 up until we get to the time t equals 30 seconds. And then, since the acceleration at that point goes to 0, the velocity will be constant from that point on. And so that's going to be a horizontal line like this. So that's our acceleration versus time, velocity versus time. And then the next thing to draw is the position versus time. Since we're actually trying to find the total distance traveled, this last one is going to be the important one. So the position versus time is going to look like this. So here's my time axis, here's my position. And so what we'll see is that since the acceleration is non-zero for the first part of the motion, we know from our kinematic equations that the distance is going to increase quadratically at that point. Once we get to constant acceleration, once we get to 0 acceleration, we have constant velocity, which means that the distance is going to increase linearly with time. And so if we look at the distance versus time graph, if I go up here to t equals 30 seconds, first I have a quadratically increasing position, which will look kind of like a parabola. And then at this point here, it becomes linear for the rest of the motion. Okay, so now that we have that, that sort of gives us a mental image of what's going on. Throughout this problem, I've been breaking things into the first 30 seconds and the second part of the motion. So this naturally suggests that there are two separate epochs in terms of how we describe this motion. We have constant acceleration here, and we have 0 acceleration there. And so we also know that from this graph that if I linearly increase the velocity until I get to t equals 30 seconds, the velocity that I have at the end of this acceleration is equal to that constant velocity that I have going forward. And so this allows us to kind of break things up into two separate pieces. If we can solve the first piece and describe that, that gives us the entrance into solving the second piece of the problem. So what we really need to do first is to find the velocity at this point here. That will allow us to connect these two pieces, and that will allow us to then go on and try to understand what the position is, which is what we're actually after. Okay, so there are two ways to do this. So let's look at the first one. So we're looking at the first epoch of the motion here, and we'd like to look at position versus time. And we have an equation for that. We know that the final position is equal to the initial position plus the initial velocity plus 1/2 times the acceleration times the time squared. So as we go through this, now we can plug in our original conditions for this problem into this equation. So let's assume that we start at an initial position of 0. We have no initial velocity as we go through this, so the initial velocity is also 0. And we have an initial acceleration. So the only non-zero term in this equation is this one here, and my initial acceleration is 3 meters per second squared. So if I take that and I finish writing this equation, I can write that x final is equal to 1/2 times 3 meters per second, which is the acceleration, times the 30 seconds that I travel squared. And that will give me the final distance at the end of the first epoch of this motion. And so if I go through that and put all of that into this equation, then the final position, calculating it out, is equal to 1,350 meters. And so that tells me where I ended up using my original equation here. One of the things that we can do as well is we can figure out the final velocity after that initial segment, we know that the velocity versus time is also given by one of the equations that we derived. And we know that that is equal to velocity final is equal to velocity initial plus acceleration times time. That was another one of the equations. And since my initial velocity is equal to 0, then my final velocity is going to just be equal to my 3 meters per second squared times the time that I'm traveling, 30 seconds. And so solving this out, my final velocity is going to be equal to 90 meters per second. So we've set this up. This is now the position at the end of the first epoch and the velocity at the end of the first epoch. And so now we can carry this forward to solve the second half of the problem.